Previously, we looked at calculating the total error with our cross-entropy function and implemented it inside of our code. The idea is that with some random displayed data, the computer will display some random model. Based on that model, it needs to calculate the error as we did previously. But now what we'll do is use gradient descent to minimize that error and obtain a better linear model which better classifies the data. And we keep doing that over and over through many iterations until we obtain the perfect line. To minimize the error, what we need to do is first take its gradient, its derivative with respect to the weights. If we were to add the gradient to our linear parameters, weight 1, weight 2, and the bias, what that will do is result in new weights and biases of a line with a much higher error function. Accordingly, by subtracting that value, this tells us the value that's going to decrease the error function the most. Ultimately, this results in a linear model with a smaller error. That new linear model, once again, will calculate its error function, subtract its gradient, and keep doing that over and over, minimizing the error function, eventually obtaining a line with small enough error that correctly classifies our data. Unfortunately, in Python, we're not able to simply take the derivative of the error function, but have to actually derive the equation ourselves and then code it. If you're interested in the math behind how the equation is derived, I've included it in the subsequent article. But to keep things short, the gradient of the error function will simply be obtained by multiplying the coordinates of the points by the prediction minus the original label divided by the number of points. Subtracting this value from our linear parameters results in new updated weights for a new line, which will thereby have a smaller error function than the previous. One more thing we're going to do is, we want to take very small leaps from one line to the other. We don't want the value of our lines to change drastically in each iteration. We know that subtracting the gradient adjusts the weights of the line in the direction which gives us the least error, but we don't want the line to move too far in that direction. So we'll scale our gradient down by multiplying it with what's called a learning rate, which is normally a small value of, let's say, 0.01, something small. This ensures that we're still going in the direction that best minimizes our error, but we're doing it in small steps. And that's the formula for gradient descent. Let's apply it to our code in the next lesson.